Alright guys, welcome to the third installment of Miss Claire's Never at School in May. Today I'm going to go over intermolecular forces, something that you investigated or are going to investigate a little bit on your own when you do that intermolecular forces inquiry assignment. But I thought I'd go through these slides and give you guys a little bit more elaboration, maybe a little more emphasis on the kind of language that IB is interested in when we're discussing intermolecular forces. So that said, here are the IB Chem Guide expectations for intermolecular forces. So the essential idea is the physical properties of molecular substances result from different types of forces between their molecules. And as we get into them more in depth, we see these key terms here, London, and then in brackets dispersion forces, dipole-dipole forces, and hydrogen bonding. So those are the three types of intermolecular forces that you need to focus on. And then you should understand that these types of forces vary in strength. So London dispersion forces are the weakest forces. Dipole-dipole are kind of in the middle, and then hydrogen bonds are the strongest. Okay, and then in terms of application and skills, you should be able to look at a chemical formula, deduce Lewis structures, shape, whether or not the molecule is polar, and then make predictions about the physical properties based on the anticipated intermolecular forces. Okay, and then there's just a little more detail here about London dispersion forces. I'm not going to read through that quite yet because you probably don't have enough context to really know what they're talking about here, but you should probably revisit this at the end or later on just so you are aware of what London dispersion forces refers to and then what van der Waals forces, which is like more of an umbrella term, refers to. And then just know that we're also going to be discussing something that's really from topic 4.3, which is prediction of molecular polarity from bond polarity and molecular geometry. That'll be sort of the first half of this PowerPoint that we're looking at that because it's a bit of a tricky skill to work on. Okay. So, we've already talked about polar versus non-polar bonds. So in a non-polar bond, like in the hydrogen molecule, the electrons are shared equally. So there's no unequal distribution of charge. Okay? Whereas in a polar bond, like the one we would see in the hydrogen chloride molecule, the chlorine is more electronegative than the hydrogen, meaning that the electrons, if we're sort of looking for the electrons at any given time, they're more likely to be found near chlorine. We're talking about the pair of electrons that make up the hydrogen-chlorine bond. They're more likely to be found close to chlorine rather than close to hydrogen, and sort of the relative size of these clouds here are supposed to represent that. So that means that the chlorine side of the molecule is going to have a slightly negative charge, the hydrogen side a slightly positive charge, so we call that a polar bond. All right. And then this is just another way of sort of expressing that. So talking about that idea of electronegativity difference, in a non-polar bond, the electrons are shared approximately equally, which means that you have an electronegativity difference in the range of 0 to 0.4. In a polar bond, there's an unequal sharing of those electrons, which gives you that electronegativity difference between 0.4 and 1.8. And then if it's an ionic bond, then you have a larger electronegativity difference, something between 1.8 and 3.3. And then this sort of relative size of the ions or the atoms participating in these bonds is supposed to show the electron density around them. So if there's greater electron density on one side of the molecule than the other, that might be a polar bond, or if the electron density is so much greater on one side than the other, then we consider that an actual electron transfer. It's an ionic bond. Okay, but there's a spectrum of bonding here. Okay, now what we're going to be focusing on today is obviously more the difference between these two. We've already talked pretty in depth about ionic bonds. So then here's some examples of compounds and different types of bonds. So obviously if you have a diatomic molecule where both atoms are the same, then the electrons have to be shared equally because they have equal electronegativities. You see the electronegativity difference obviously there is 0, so you have a non-polar covalent bond. Okay, but then as we look at compounds where the electrons are shared unequally, so like hydrogen bromide or hydrogen chloride, those electronegativity differences are in the polar covalent range. And then in compounds that we sort of expect to be ionic compounds, sodium chloride, magnesium oxide. We see electronegativity differences definitely in that ionic range. Okay, so this is a new idea, but it doesn't often conflict with what we already knew about covalent versus molecular bonds. Ionic bonds tend to be between metals and nonmetals, and covalent bonds tend to be between only nonmetals. Okay, there are instances where that rule is broken, but we don't really have to focus on those exceptions. So I'm going to give you some time, pause the video, take a look at these 4 examples of bonds, and use electronegativity difference to classify them as nonpolar, covalent, polar, covalent, or ionic. So pause the video, grab yourselves a data booklet if you haven't already, and find the electronegativities to figure that out. And then welcome back. So hopefully you took a little bit of time to check those out, and you got something like this. Okay, so those are the answers there. And it's pretty straightforward, I think. Okay, so now we're going to extend the idea of polar or nonpolar bonds to talking about overall molecules. Okay, now sometimes a molecule will contain polar bonds, but the overall molecule is not polar because we have to consider both the polarity of the bonds and the shape of the molecule. Okay, so we're going to combine these 2 ideas together to decide if molecules are polar or nonpolar. So the first thing we want to do is, or the first thing we're going to do here is consider the bonds. So in this case, hydrogen chloride, this is an example we've already done. It's a simple diatomic molecule, and it definitely does have a polar bond. The electronegativity difference is definitely in that polar range. Okay, so then I want to consider the shape. Okay, and what I look at here is the fact that there's only one bond and the electrons are clearly being pulled in this picture to the left side of that bond. So there's what we call a net dipole. And often we illustrate that with an arrow. Okay, so I've included an arrow here to show the direction that the electrons are being pulled. So then, yeah, there is a net dipole. The molecule is polar. Okay, classic example of a polar molecule. Pretty straightforward. Okay, you might want to pause the video here and make sure that you sort of follow those steps before we move on to the next example. So here's a second molecule, carbon dioxide. So the first thing we want to do, obviously, look at the bonds. And in this case, we've got an electronegativity difference of 1 between carbon and oxygen. So yeah, it's a polar molecule. Now we want to consider the shape. Okay, so we know from our VSEPR theory that carbon dioxide has a linear shape, which means if I draw in those arrows to represent how the electrons are being pulled, they're being pulled equally in opposite directions. So even though the bonds are polar, there's no net dipole. There's no one side of the molecule where the charge is slightly negative and then the opposite side is slightly positive. So this is not a polar molecule. And that actually explains a lot of the properties of carbon dioxide, right? It's a gas at room temperature, meaning that it has relatively weak intermolecular forces. Okay, and we'll start tying all those ideas together as we progress through this. Okay, again, you can pause this video at any point. Just if you guys are in class watching this, you can ask to have the video paused to review something or rewind or whatever. Okay, let's look at another example here. This time, ammonia. So here, once again, considering the bonds, electronegativity difference is in that polar range, okay, 0.9. Now we want to consider the shape, and hopefully you remember ammonia again is an example that came up in the VSEPR theory videos. So it has a trigonal pyramidal geometry, meaning that you have sort of all the hydrogens in one plane, and then the nitrogen. So all these hydrogens are sort of in one plane, and then the nitrogen is a bit above them. So if I draw in arrows to represent how the electrons are being pulled, they're being pulled towards that nitrogen, which does create a net dipole. Okay, and that's really because of this lone pair right up here, right? Without that lone pair, the hydrogens would all be on the same plane. These dipoles would cancel out. But with the lone pair up here, it makes it that trigonal pyramidal rather than trigonal planar geometry. So we do end up with a net dipole. So yes, ammonia is a polar molecule. All right. Another example, pretty straightforward one. This one is easy, kind of easy right off the bat because we look at the bonds and we see that the carbon-carbon bond has an electronegativity difference of 0, so it's definitely not polar. And then the carbon-hydrogen bond is actually a classic example of a nonpolar bond as well. Its electronegativity difference is only 0.4. So we actually don't even have to consider the shape because the bonds aren't polar, so the molecule is not polar. Now, when you work through your intermolecular forces assignment, you will find an example where the bonds are nonpolar, but if you Google that molecule, you will find that it's still described as polar, and it has something to do with lone pairs. So just know that it's not part of the IB expectations for you to be able to explain that, but if you want to do a little bit of research and give a more in-depth answer to that question in the Google form, go ahead. That's very cool. Okay, so here's just a summary table that sort of gives you an idea of how you can use shapes to predict polarity. And in terms of the IB content, you actually won't be looking at molecules with a more complex geometry than a tetrahedral basis shape. So this is a really helpful table for this. Okay, so you can pause the video and maybe take a look at this. I want to point out one detail because it can be, you might not notice it on first glance, but so X represents one type of atom and Y represents another type of atom here. So if you have an X and a Y, that might change the polarity. Whereas if you have all X's, then it might be a perfectly symmetrical molecule with no polarity. Okay? And then just one more set of examples to try. So I do recommend pausing the video here, giving these molecules a draw. So there's actually quite a bit that goes into this. You want to first draw the Lewis structure, then you want to look at each of the bonds, calculate the electronegativity difference to see if any of those bonds are polar. If there are polar bonds, then you want to come up with a specific molecular geometry using Vesper theory and look at the overall shape of the molecule to decide if it's polar or not. Okay? So pause the video, take a second to do that, and then I have some answers for you. I believe these are related but not identical molecules that might give you some ideas of the answers. Okay, so I'm going to stop it here and I'm going to make a part 2 that continues on with more in-depth exploration of intermolecular forces.